We today have 3 remote centers connected for this course on industrial automation and robotics. First is Gyan Jyoti Group of Institutions, Banur. Then Punjab University Regional Center, Hoshiarpur, and SCS VMV University, Ennathu, Kerala. And we have around 6 participants in our studio. My name is S.S. Gandhi. I am professor in mechanical department in this institute. So I'm the coordinator of this course. I'll be connecting this course. We'll have some experts also from industry organizations. So, and I had sent the timetable for the course to all the remote centers. Now, before we formally start the course, let me invite the coordinators at the respective centers to introduce their centers. The coordinators are requested to introduce themselves, their institute, and the number of participants participating in this course. So first of all, I invite Gyan Jyoti Group of Institutions, Banur. The coordinator at Gyan Jyoti Group of Institutions.
Good morning, sir.
Good morning, Ji.
So we thank Dr. Sukhdeep Singh Dhami for making us being part of this event on industrial automation and robotics.
I have a request. You please take the seat. We cannot see you actually. You are too close to the camera. You can take You can. We cannot see you because you are too close to the camera. So please take a seat in front of the laptop so that we can see you also.
Basically, we are using a camera which is fixed to the mic only. So basically, we have to use this mic.
You need not come very near to the mic. Your voice is very audible.
Right.
So you can have a seat in front of the camera if possible. Otherwise, I can see some participants, but I cannot see you actually. थोड़ा सा आप पीछे होके बात करें और पीछे हो जाइए. Perfectly all right. Now we can see you. Okay, now we can see you. Now you can speak.
For organizing this event on industrial automation and robotics. We have around 23 participants from electrical electronics, ECE, CNC and mechanical. Sir, automation or automatic control is the use of various control systems for operating equipment such as machinery, processes in factories, boilers and heat treating ovens. Usually on telephone network, steering and stabilization of ships, aircraft and other applications with minimal or reduced human intervention. The biggest benefit of automation is that it saves labor. However, it is also used to save energy and materials and to improve quality, accuracy and precision. So basically, I thank NIDR on behalf of Gyan Jyoti Group of Institutions in making us be part of this event and innovative session. So basically, I thank again, sir.
Okay, right. Dr. Neeraj Sharma?
So on behalf of Dr. Neeraj Sharma, I am Sharad Sharma speaking on behalf of him.
No, you are Sharad Sharma?
Yes, sir.
Okay, Sharad. So I talked to you on the phone. Okay, thank you for the introduction.
Thank you, sir.
Okay. Next, I will invite the coordinator at Punjab University Regional Center, Hoshiarpur. Okay, so I think we have to wait for Hoshiarpur. So in the meantime, I request the coordinator at SCS VMV University, Ennathu, Kerala. to
Sir,
please introduce your center.
sir, good morning, sir. This is Shivakumar from SCSBM University.
Good
So
morning.
I'm Tamil Nadu, not Kerala, sir. Actually,
Mm-hmm.
yes. Um,
Oh,
Beside
sorry,
the
Tamil Nadu. Okay, I'm sorry. Sorry.
Tamil Nadu, sir.
Right. Uh,
So
please.
actually, we
Uh,
received a response from 34 members. Still,
okay.
they are coming. Actually,
Okay.
uh, some of some of them are in class. Actually, they after the class they will come surely. Maybe at 11 o'clock they will be here only.
Okay. Otherwise, approximately 30 participants will be attending the course.
No, actually, we are receiving a response as a form based registration.
Okay.
Maybe
So,
this time, how many members are coming
sir,
here and attend?
by lunchtime you will be able to tell.
Yes, sir. Thank you, sir.
Is Sharpo connected?
Hello. Hi, sir. We are from Hoshiarpur. Is it audible to you?
Yeah, 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 absolutely audible.
I'll hand over the mic to coordinator CSC and IT, who is coordinating this workshop.
Good morning, sir.
Good morning.
So this is Dr. Supinder from PUSS GRC for Shahpur. We have around 35 candidates who will be participating in this STC.
Okay.
Anything
Okay.
else? We are
Uh,
almost ready, but I don't know why that they are not being
we can
added
hear,
on.
you, but I think your video is not visible to us.
So that we are trying. Within few minutes, it will be done, sir.
Otherwise, our video and our audio, is it clear?
Yes, sir. It's absolutely clear, sir.
Okay. Thank you.
Okay.
Okay, so we'll start with the course another 5 minutes. So please wait for 5 minutes more. Okay, so in the meantime, I will request the participants in our studio to introduce themselves. So we have total of 6 participants in our studio, out of which 3 are our ME students who have just taken admission, and 3 participants are from the colleges. So please, one by one. You're in CCT. CCT. Dehradun. Vineet, है ना? Yeah, Jayant. Hardeep. हाँ जी, वो भी आज ज्वाइन कर रहे हैं. You can keep your bags on the table. दीपिका मैंने कॉपी कर लिया है इसके ऊपर. बस पीपीटी चला ली है. ठीक है. They are connecting or it will take time? कितना टाइम लगेगा? Huh? Okay, friends. So we have another center. It's Gandhi. Gandhi. Okay. Gandhi Academy of Technical Education from Berhampur, Odisha, who are also joining us. So they will take probably 3-4 minutes more, and then we'll start with the technical presentation. So I had sent the course timetable to all the 4 centers. So today our first session before lunch will be on introduction to automation. We'll have a tea break also in between at 11:15 for 15 minutes. After our lunch session, we'll have basics of digital logic. Then tomorrow morning sessions are on programmable logic controllers, and afternoon session is on simulation of PLC applications. Then Wednesday before lunch we have sessions on microcontrollers, and afternoon session will be introduction to robotics. Then Thursday morning we'll have full session on robotics, that's configuration and kinematics. And then Thursday afternoon we'll have fundamental of control systems. And Friday morning we'll have demonstration of PID control and automation case studies. Now, because a number of experts will also be participating in the course, so sometimes as per the availability of the experts, although this timetable has been framed as per their availability, but sometimes due to some urgent work, we may shift a few sessions here and there, but we'll try to keep the flow of the program as per the requirement, and we'll inform you well in time about any shifting of the session.
चल हो जाना ठीक एक बार स्टार्ट किया फिर चल रहा है क्या
So have they joined? The Sharpur video is available or not yet? शारपुर वाले और गेट वाले थे कनेक्ट हो गए ओके ओके शारपुर इज नाउ डिस्कनेक्ट ओके ओ मे बी दे आर ठीक है Okay friends, so we will start. So now we have 4 centers connected or they'll be joining very soon. So in the introductory session, we'll discuss the fundamentals on industrial automation and robotics. So madam, you can switch to presentation. So as all of us know, okay, in this presentation, this is the layout. We'll have introduction to automation, then a brief introduction to actuators, something brief about PLC and robotics. So in the first session, I will not be going through the whole of the presentation, but I'll go through as is required in the introductory session. So as all of us know, automation is doing something without or with minimal human assistance. So automation can be defined as the technology by which a process or procedure is accomplished without human assistance. The term automation was coined by a person, Del Harder, who was working in Ford Motor Company in the year 1946. For implementing automation, we need a program of instructions combined with a control system that executes the instructions. So when we talk of control system, the control system will consist of primarily 4 components: actuators, that will actually do the work, sensors which will provide the feedback about the various parameters, the controller which will receive information from sensors and accordingly switch on or switch off the actuators or change their speed, etc. And the fourth major component is the signal conditioning. Now if we talk of levels of automation, then we can divide the automation into 5 levels. Automation robotics? No, that is upstairs. Okay. So levels of automation we have at the topmost level, enterprise level, then plant level, then cell or system level, machine level and device level. When we talk of enterprise level, there we have major functions which are required for planning, marketing, accounting, design, research, master production scheduling. That is the functions which are concerned with the top management, or you can say about the sales and procurement. Right? At plant level then we talk of planning the manufacturing. So here we have order processing, process planning, inventory control, purchase, material requirement planning, shop floor control and quality control, etc. Then we come to actual manufacturing where we have cellular or system level. Here we have part dispatching and machine loading, coordination amongst the machines, material handling systems, and collecting and evaluating inspection data. So as a cell or a group of machines will consist of a number of machines. So next is the machine level. So within a machine level we have automation pertaining to sequencing, timing and overall control. So for example, in a machine we'll have sequencing, we will load a workpiece, clamp a workpiece, then a tool will start. Similarly, timing, a machining operation may be performed for a given time, and the overall control of the individual machines. And finally we have the device level where we have control of individual actuators. At this level we talk of actuators, sensors and other hardware elements like signal conditioning and controllers. So in this course we are mostly focused on the device level, and where we will learn that how different components they are combined to form the fundamental of automation. Now talking of fundamental of automation, as all of us are aware, today all the machines are a combination of mechanical, electrical, electronics, software, etc. So the foundation of automation is, we can say, mechatronics, which is integration of mechanical, electrical and microprocessor based control systems. Any process that we carry out is basically mechanical because all manufacturing will require some kind of machining or forming or joining, which has to be performed by actuators. Now actuators may be electromechanical or they may be electro-hydraulic or electro-pneumatic, and their control is primarily microprocessor based along with the software. Right. So mechatronics term was coined by a Japanese engineer, Mr. Tetsuro Mori from Yaskawa Electric Company in 1969 to reflect the merging of mechanical and electrical engineering disciplines. So Yaskawa Electric Company is still a very famous company for electric motors and robots. The term mechatronics gained legitimacy in academic circles in 1996 with the publication of the first referred journal IEEE and ASME Transactions on Mechatronics. So this journal is a joint publication of 3 IEEE societies and 1 ASME society: IEEE Industrial Electronics Society, Robotics and Automation Society, Laser and Electro-Optics Society, and ASME's Dynamic Systems and Control Division. Now going a bit more through the history, if we talk of the decade of 1917s, so there mechatronics was concerned mostly with servo technology used in products such as automatic door openers, vending machines, and autofocus cameras. So these applications were simple in implementation. The approach encompassed the early use of advanced control methods. In the next decade of 1980s, as microprocessors became smaller yet powerful, engineers began to embed microprocessors in mechanical systems to improve their performance. Numerically controlled machines and robots became more compact, while automotive applications such as electronic engine controls and anti-lock braking systems, they became widespread. Then in 1990s, the internet or the communication technology was added to the mix, yielding products that could be connected in large networks. This development made functions such as the remote operation of robotic manipulator arms possible. Micro-electromechanical systems, commonly known as MEMS, such as tiny silicon accelerometers that trigger automotive airbags, arrived on the scene. Now, in the past 2 decades, that is in the decade of 2000 and in the present decade which is going on, something more has actually now come in, which is not present in my presentation, but otherwise I will discuss it. So in 2000, technologies such as data mining, cloud computing, they arrived on the scene. And internet also, it became pervasive, and I think in the decade of 2000, we could not believe that life is possible without internet. As a result of this, in the present decade, that is 2010, another technology known as IoT, that is Internet of Things, is now fast becoming a reality, and by 2020 or 2025 it is estimated that more than 50 billion devices will be on the Internet of Things network. In fact, the manufacturing industry is already awake to this situation, and in 2010 in Germany a standard called as Industry 4 standard has been proposed. So Industry 4 has been named so because now they are calling it the fourth revolution in industry. The first industrial revolution is attributed to steam power. When steam power was, they started to use steam power for industrial machines. Then second industrial revolution is concerned with the electrical energy. The third with electronics, because the miniaturization of electronics, it resulted in automation going to a very, you can say, large level. So the fourth is now called as Industry 4 revolution, because here now we have the automation, the data mining, the cloud computing and Internet of Things, which is going to revolutionize the manufacturing industry. Now coming back to our present course on automation, First of all, let us see an example of servo feedback. Right. Now, when we talk of manufacturing, as I said, we may have a machining, a forming, or maybe a joining process. Even nowadays, we have a rapid prototyping technology which is called as additive technology. Even if we consider that, the fundamental is that a workpiece will move relative to a tool. So in this application, let us consider a work table on which a workpiece is to be mounted, and this work table is to be moved through a distance x, which is a function of time. Now the first problem is, or the first challenge is, how to move the work table. Naturally, if we want to move a table or a chair on the floor, we can use muscle power, but when we are talking of a machine, the work table will be moved by an actuator, so very commonly by an electrical actuator. So here we see electric motor which is coupled to the work table. Now the coupling is through lead screw mechanism. Electric motor is now electromechanical device. The lead screw is a purely mechanical device along with the work table. The electromechanical motor will provide us a mechanical motion in the form of a rotary motion when electrical energy is given to it. The lead screw is designed to convert the rotary motion into linear or translational motion, and accordingly the work table will move. Now here our problem is to move the work table through X. So if we keep on rotating the motor, ultimately the work table will be stopped by mechanical stops on the two extremes. But not considering the mechanical stop, say we want to move it through 5 millimeter or 5 inches, anything, that is small x. So to move it through a certain distance, it is very fundamental that we measure that how much that table has moved. So for measuring, we will need some kind of a sensor which will measure the displacement of the work table. So the sensor will keep on measuring the instantaneous displacement of the work table and provide information to the system. Now, as an automation, it is a controller which will control the whole process. So it is fundamental that the sensor that we use is a kind of sensor which will convert the mechanical parameter into a electrical signal. So this electrical signal will be then given to a controller, and to the controller the operator or the user had already given a position command, that is how much X we want the work table to move. For example, in the case of a microwave oven in our homes, to the controller we provide normally the time for which we want the operation to take place. And when we start the microwave, the instantaneous time is measured, and when the instantaneous time becomes equal to the time that the user has specified, the microwave will stop. So the same thing is here. The user has provided to the controller the reference position, that how much displacement the work table should go through, and the sensor now provides the instantaneous position of the work table. So, but if we look at our this slide, from the sensor to the controller, the connection has been shown by a dashed line. Why? Because we need some other thing in between the sensor and the controller, that is signal conditioning. Because we should remember that the output of a sensor may not be suitable for a controller. Suitable in many forms. For example, The output of the sensor may be a very small voltage which may not be discernible for the controller. The controllers are all electronic devices, electronic circuits consisting of microprocessors and other ICs. So they may be working on 5 volt, 10 volt, 12 volt, etc. Whereas the output of a sensor may be in millivolt or even microvolt. So first thing is that the output of the sensor has to be amplified. Second is the controllers are all digital devices which work on digital signals, whereas a sensor in this example, since it is measuring displacement, which is an analog variable, so the output of the sensor will be analog. So this analog signal has to be converted into a digital format. So at least these two conversions are required, some kind of amplification and conversion from analog to digital. Some other conversions or other functions are also required. For example, filtering, because the output of the sensor may contain some noise also, so that has to be filtered out so that only the desired signal is given to the controller. So all these things, amplification, analog to digital conversion, filtering, and maybe a few more, they are covered under the heading of signal conditioning. Now on the output side, the controller is connected to the motor again through signal conditioning circuit, so which may again consist of digital to analog conversion, some kind of amplification or attenuation, because there will be driver circuits for the motor. So in this manner, what we get is a closed loop system. So in the closed loop system, now we have a process which is the work table, which is to be moved through a certain distance. For doing that, we have the actuator, that is the motor, which is electromechanical device, and we have sensors, signal conditioning, and controllers, which sensors may be electromechanical or you can say electronics. Signal conditioning and controllers will be only electronics along with some software part. So what we see is that whenever we are talking of an automation system, the components from all the branches of engineering will play their role. So typically we have seen that at least the three fundamental components are controllers, actuators, and sensors. Now controllers can be a variety of types: microcontrollers, digital signal processors, programmable logic controllers, single board computers, personal computers. Right. Similarly, actuators, they may be based on electrical energy or they may be fluid power actuators, and variety of sensors for measuring different types of parameters like position, proximity, displacement, velocity, acceleration, force, pressure, liquid flow level, temperature, light, humidity, any gas, composition, anything. So that means an automation system consists of all type of components: mechanical, electrical, electronics, and software. So talking of purely mechanical components, we may have pneumatic and hydraulic actuators, kinematic chains, cams, gear trains, belt and chain drives, bearings, etc. Electrical, we may have solenoids for small movements, for example in fluid power control valves, then AC motors, DC motors, stepper motors, and we'll have a different type of electronic component like operational amplifiers, analog to digital converters, that is ADC, digital to analog converter, that is DAC, filters, data acquisition systems, controllers, etc. Now, actuators are primarily electric or hydraulic or pneumatic. So what you see on the computer screen is a brief comparison between three types of actuators uh, on different you can say parameters like energy source, energy storage, distribution system, energy cost, actuator, force and hazards. Electrical energy, electrical actuators, they take their energy from outside. That is from we in our industry or in our homes we receive the electrical energy from outside from a power station through a grid. Hydraulic and pneumatic actuators are electric motor or diesel engine driven. Energy storage is limited in electrical actuators. We can store energy in batteries. In hydraulics also it is limited. In the form in accumulator we can store oil at high pressure, but it is good in pneumatic systems. We can store energy in large reservoirs. That is, the compressed air can be stored in large reservoirs. Distribution system is excellent with electrical systems because there the losses are minimal. In hydraulics, it is limited. In pneumatics, the distribution system is good in between the electrical and hydraulic systems. Energy cost is lowest in electrical systems and highest in pneumatics. Actuators, AC motors are very cheap. In fact, they are called the workhorse of the industry. In DC motors, we can have good speed controls and we can also have short linear motions with solenoids. In hydraulics, we have low speed but with very good speed control, and we can have large linear movements. Similarly, in pneumatics also we can have large linear movements directly. We have a wide speed range, but the speed control is difficult, and even position control is difficult because of the compressibility of the air. Force wise, electrical systems give a low power to weight ratio. Hydraulic systems give the highest power to weight ratio, and pneumatic systems give medium power to weight ratio. Hazards wise, electrical systems, there is a danger of electric shock. In hydraulic system, if there is oil leakage, it is dangerous. People can slip, oil can catch fire, and it also doesn't look good. In pneumatic systems, we don't have any hazards except for noise when the air leaks. So this is a very brief introduction to fluid power systems. Hydraulic systems, they use incompressible medium like oil. Their operating pressures are high, 150 bar. So as our atmospheric pressure is nearly 1 bar, so you can see the operating pressures are quite high. But they produce noisy and wear-inducing shocks in the piping as it works at high pressure. Pneumatic systems, they use compressible medium, mostly air. Operating pressures are 10 bar, 15 bar, 20 bar, and they are softer in action because of the again air compressibility. In fluid power systems, the basic elements are power sources, cylinders, control valves and fluid lines. In power sources, hydraulic systems will use hydraulic power packs, and pneumatic systems, they require air compressors. Cylinders can be single acting, double acting, rotary also. Control valves, we require three types of control in fluid systems. One is directional control. That is because cylinder has to be moved in two directions, in the forward direction and in the backward direction. Then flow control. The flow of oil or air has to be controlled so that the speed of the piston in the cylinder can be varied. And pressure control is required because so that we can have different pressures and hence different force available at the piston for doing the work. Then to connect the different components we need fluid lines. There may be piping, there may be tubing. So it's a very simple line diagram of a single acting cylinder where we have a barrel. Inside the barrel there is a piston. For a single acting cylinder there may be spring on one side of the piston. So if we push the air or oil into this side, the piston will move forward, and when the fluid is taken out, then the spring will push the piston back. For a double acting cylinder, We have two ports, say X and Y. So when the piston is to be moved in the forward direction, we will push the fluid in through X and take the fluid out through Y from the other side of the piston. The piston will move forward. And to move the piston backward, we will push the fluid in through Y and take the fluid out through X. So this is not required now. Now, as it's an introductory lecture, so I would like to show you some animations about fundamentals of how hydraulic or pneumatic systems work, because from there only we will develop a understanding of that how does the controller play their part in automation. Now if you look at this diagram, what you see is a single acting cylinder. It's a pneumatic cylinder with a piston and a spring on one side. The other side of the piston is connected to a directional control valve, which in this case is a 3x2 valve. Now it is called 3x2 because it has three ports. The first port is the pressure port, which is connected to the air compressor. The second port is the working port, which is connected to the cylinder. And the third port is the exhaust port through which air can be released to the atmosphere. The valve has a body in which the ports are made, and inside the body there is a spool. This spool can be moved down by applying a mechanical force here or a manual force, and it can be moved up by this spring. So when no mechanical force is acting on it, the spring will keep the spool in this position, and in this position, as you can see, the pressure port is blocked. The pressure port is blocked and the working port is connected to the exhaust port. Therefore, the pressure is atmospheric in this area, in this tube, and on the left hand side of the piston. When we will move the spool down, the larger diameters of the spool will block the exhaust port, and the pressure port will get connected to the working port. The compressed air will flow into the cylinder and the cylinder piston will move forward. So let us see the animation. So when I run the animation, you will see immediately a dark blue color occupying this portion. So the dark blue color indicates compressed air. So as you saw in the animation, that when the spool is in this position, the compressed air is blocked here. But when the spool moved down, the compressed air flowed into the cylinder. So we can see it once more, then we will proceed further. Okay. Now let us see a double acting cylinder. So in this we don't have a spring in the cylinder, so that means air has to be pushed in on two sides of the cylinder depending upon which direction do you want to move the piston. So for this now we are showing here that we are using two 3x2 valves. To move the piston forward, we will operate this valve so that compressed air from the cylinder through the T connector and through this valve will flow to this side of the piston, and the piston will move forward. And when we want to move the piston backward, then we will operate this, the other valve. So then the air from the compressor through the T connector will flow through this valve and go into the cylinder on the other side of the piston, and the piston will be pushed backward. So let us see its animation. Right. So what we just saw, that when we start the simulation, when both the valves are closed, the compressed air is blocked here as well as here. So only when we operate a particular valve, accordingly the air flows into the cylinder and then the cylinder piston moves. Now up to this point we have used valves which are purely mechanical. Now in the next step we have a electromechanical system. Here the cylinder is same, that is double acting, but now the valve is different. Number one, instead of two valves we have only one valve. Number two, the configuration of this one valve is different. So this is a 5x2 valve. Why? Because it has 5 ports. First is the pressure port, then second and third are the two working ports, then fourth and fifth are two exhaust ports. So we say 3x2 when the valve has 3 ports but 2 positions. So if we recollect our previous animations, the valves had only 2 positions. In one position, the pressure port was connected to the working port. In the second position, the working port was connected to the exhaust port. Here also we have 2 positions. In one position which you can presently see, the pressure port is connected to working port A, and the second working port B is connected to the exhaust port S. Whereas in the second position, when this spool will be moved towards left against the spring force by this electrical solenoid, what will happen? Pressure port P will get connected to B and working port A will get connected to the second exhaust port, that is R. Now this electrical solenoid it requires electrical energy which will be provided through the switch. So when the switch is open, the coil is not energized and the spool remains in the position that is being presently shown. But when the switch is closed, the circuit is completed, the coil will be energized. So the coil will then pull the spool towards the left against the spring force and the position will change. Let us see the animation of this. So what we saw here was that since this is the position when the coil is not energized, so when we start simulation, air from the compressor moves through the port P to the port A into the cylinder and the piston moves forward. When we operated this switch, the coil was energized, it pulled the spool towards the left, then the port A was connected to exhaust port R and pressure port P was connected to a working port B, and accordingly the piston moved backward. So let us see the animation once more. So now what we have seen is that we started with a single acting pneumatic actuator which was being controlled by a single 3 by 2 manually operated directional control valve. Then we saw the operation of a double acting cylinder operated by two 3 by 2 manual directional control valves. And now we have come to electro-pneumatics, where the valve, directional control valve, is not operated manually but by electrical means. Now the next step is incorporating the controllers, right? And basically, because here if you see, this switch is being controlled manually, right? So the construction of the switch shows it's like a doorbell switch. So do you have to apply a force against the spring, and when you apply the force against the spring, the contacts are made, the circuit is completed, and the solenoid is energized. Similarly, when you release the force, the spring pushes the contacts up, thereby the circuit is broken or the circuit is open and the coil is de-energized. Now we want this switch to be operated not manually but automatically, so that will be done by a controller. So we can have a controller which may operate a relay. So this will be replaced by a relay, or it may be replaced by a electronic switch. So next we will see some videos. In videos we will see a controller operating the pneumatic actuators, and those videos have been made in our lab only. So in this videos you will see a PLC being used. So as I said that in this session I will skip some of the slides because we will deal in detail with the PLC or programmable logic controller in tomorrow's session. But a very brief introduction. So what is a programmable logic controller? It is a digital electronic device that uses a programmable memory to store instructions and to implement functions such as logic, sequencing, timing, counting, and arithmetic in order to control machines and processes. Now a computer is also a digital electronic device. A computer also uses a programmable memory. A computer can also store instructions, and a computer can also implement all these functions. The difference is that PLCs are designed to operate in industrial environment, that is under high temperature, vibrations, etc. So in brief, they are more rugged as compared to computers or laptops. Otherwise, technically they are similar to PCs only. They have their microprocessors, they have their RAMs, their ROM, input output ports, and all the associated circuits. So if we just look at very briefly at the history of PLCs, the early machine control was through cams, gears, levers, etc. Then came the wired relay and switch control elements. Then programmable logic controllers came into existence in late 1960s, and this was done by industrial environment, automobile, high temperature, vibrations, etc. Okay. Initially, these PLCs were called programmable controllers or PCs. But in 1980s, when PCs became personal computers became very popular in the world, and PLCs were only confined to the industries, so the term PC was then generally associated with a personal computer. So therefore, the programmable controllers nomenclature was changed to programmable logic controllers, and now they are called as PLCs. So this is a photograph of the PLC that we have in our lab. So in the videos also you will see this PLC in action. In general, this is the block diagram of a PLC. A PLC will receive initially these PLCs were called programmable controllers or PCs. But in 1980s, when PCs became very personal computers became very popular, and is there a lag? Okay. Okay. So a PLC will receive inputs from the sensors which are connected to the devices, and we will have a control program or logic fed into the PLC. So based upon the logic and the sensor information, the PLC will control the output devices such as motors, relays, etc. So you can see this is a block diagram of a PLC, very similar to a personal computer. It has a CPU, it has input interface, output interface, it has volatile memory, RAM, and it has non-volatile program backup memory. So if we compare PLC versus PC, a personal computer is optimized for calculations and display tasks. And moreover, a personal computer is a very general device, control program or logic fed into the PLC. So based upon the logic, it relies on software for running different types of programs. A computer is programmed by specialists, whereas a PLC is designed for logic control and regulation tasks. It is programmed by non-specialists, and a PLC is well adapted to industrial environment. Now, for programming a PLC, we may connect it to a computer. The reason being that PLCs, they may be very small in size, and the display, the LCD display on them is also smaller in size, and sometimes they may have a very small control panel with limited number of keys. So it becomes cumbersome to program a PLC directly. So what we can do is we can easily make a program for the PLC on a computer where you have a full keyboard, screen, and an interface software for the PLC in which you will make the program and then transfer the program to the PLC. Now if we look at this elaborate block diagram of a PLC, what we see is a CPU, memory, communication channel for communicating with a PLC, with a computer, power supply, and some kind of expansion connections. And we have input and output interfaces, but here if you see in input and output interfaces, screw terminals for input lines and output lines are shown. In a computer, you have input and output interfaces in terms of USB ports, serial ports, parallel ports, etc. Whereas here we will have screw terminals where we will attach the wires from the sensors on the input side and wires from the you can say driver circuits of the output devices on the output side. So these are some of the features of typical features of PLCs. Like if we want to buy a computer, what we'll do is we specify a computer in terms of its clock speed, its hard disk storage capacity, its volatile memory storage capacity, the number of ports, especially USB ports these days. Whereas similarly in PLC also we specify that okay, what kind of power supply does it require? That is AC or DC. What is the capacity of programming? How many steps can be incorporated in one program? What is the execution speed? How many microseconds does it take to execute one step? How many inputs are there? How many outputs are there? And what is the type of inputs and outputs? Because here we may have analog and digital sensors or analog and digital outputs. Now, timers and counters are two very important parts of PLCs. So how many timers are there? Up to what time they can count? Similarly, how many counters are there and up to how much value they can count? And there may be other mathematical functions, some mathematical functions to say add or subtract the signals, or control functions like proportional integral derivative and fuzzy control, etc. So these are some major manufacturers of PLCs: Allen Bradley, Siemens, Omron, ABB, Mitsubishi, Koyo, etc. Uh, this we will skip. Next we will come to the videos for PLCs. But before we do that, we will now break for tea. It is 11:10 right now, so we will assemble again here at 11:30. So in the meantime, and after the break is over, I will also invite some questions from the centers and from the participants in the studio. So we'll break for tea now and meet again at 11:30. चाय भी लीजिए।
चल रहे हो ना उस टाइम भी मेरे लगा उन्होंने कुछ नहीं छेड़ना बस ये चल रहा है कुछ भी नहीं किया हमने
उन्होंने ही बंद किया होगा नहीं तो उनसे गलती से हो गया होगा जब उसने अनम्यूट किए ना बाकी तो उनसे हम अपना म्यूट कर देते हैं। चल रहा है ना बस स्टार्ट ही अपने में ले लेना आज मैंने तो मैंने तक नहीं सर पास रहती है सर 39 है 39 39 है ये दो है 41 नहीं चलिए नहीं वो चल रहा है देखो
होशियारपुर कैंपस।
यस मैम
सर प्लीज आप अपना माइक ऑफ रखिए, आपके माइक की वजह से बहुत डिस्टरबेंस हो रही है।
सेंटर्स आ गए चलो okay, so welcome back after the tea break. Now I will request the centers that if there are any questions up till now you can ask one by one. So we can invite the centers one by one. First from Gyan Jyoti. If there is any question from Gyan Jyoti, you may ask. हाँ जी ओके अब आप आइए
Sir, can you please explain the role of electrical engineering in electro-pneumatics again?
Okay. Is there one question or there are another question also? Is this the only question? Okay, let me ask from the center also, then I will give the answer. Okay, so any question from Punjab University, Regional Center Hoshiarpur? Please, your mic is not working. I think it is mute.
Yes, sir, we had done it earlier.
Now it is okay, yeah.
No, sir, it's okay. We are happy with that. And
Okay,
we have to listen to the earlier question.
Okay, right.
Thank you so much.
Okay, from Tamil Nadu, we have a center from Tamil Nadu. So, is there any question from the name of the center is yeah. Gate Odisha. Okay, any question from Gate? Gandhi Academy of Technology and Engineering.
Hello, good morning, sir.
Good morning.
Sir, myself Wajid Pradhan. I found out how to set timings for the DCV. For the
timing of?
For the operation of DCVs. Direction control valve.
I'm sorry, operation of?
How to set timing for the operation of DCVs.
You're talking of printed circuit boards, PCBs or what?
DCV, directional control valves.
Okay, DCVs, directional control valve. Okay. Right, okay, fine. Okay. So we have two questions. One was the role of electrical engineering in, I think, this directional control valves. Second is how to set the timings and directional control valves. So first question, as far as the role of electrical and electro-pneumatics is, that as we saw in this example, this valve is being operated by a solenoid. So in a solenoid you have a coil, and in the coil there is a conductor. Right? So when we supply a current to the coil, a force will act on the conductor and the conductor will move. So far whatever we have discussed, that is the role of electrical in electropneumatics. Otherwise, electric motors, AC motors, DC motors, stepper motors, so they are very important components of automation circuits. So when we talk of actuators, the electrical actuators are mostly used in automation, but even in hydraulic and pneumatics, because we are using electrical means to operate the directional control valves or flow control valves or pressure control valves. So switching on and off the directional control valves as well as positioning them, because there right now we are considering 5 by 2 3 by 2 valves only, but there are infinite position valves also, where the position of the spool can be adjusted so that along with the position the flow can also be controlled. So there also all this control is by means of electrical current only. So electrical engineering has a very important role to play in automation. About the second question on setting the timing in directional control valves, there can be two methods. One is that some valves they have inbuilt feature of setting the timings. Uh, so we will discuss that in the appropriate session. The second is that we set the timing in the controller and accordingly the controller will operate the valve at that time. So both these methods will be shown in our discussion. So in this week, let me just emphasize that our discussions will be through animations, videos, and some limited practical demonstration also that you can see on the camera. So what I mean to say is our focus will be on showing to you things in action, because theory you can always go through in the books. So we saw some fundamentals, we saw some animations of electrical actuators. So all this we are doing so as to have an overview of automation in this session. So we were here, this was the last slide we discussed before the tea break. Now we will see some videos. So these slides which you are presently seeing, these we will discuss in the tomorrow session when we discuss PLCs. Now let us have a look at this board that we have in our lab. What you see in this picture is a programmable logic controller which is connected to a number of actuators and sensors. First of all, let us see the actuators. Here what you see is a double acting pneumatic cylinder which is controlled by a 5 by 2 directional control valve. So I'll just take a break. Let me attach a mouse to it. Okay. Okay. So as I said that this is a programmable logic controller that you are seeing. Then we have a double acting cylinder, pneumatic cylinder, which is controlled by this 5 by 2 directional control valve. Now this 5 by 2 directional control valve has two solenoids. In the animation that we saw, there was only one solenoid. So when we were operating the solenoid, the spool moved into one position, and when the solenoid was switched off, the spring pushed the spool to the other position. Here we have two solenoids, so there is no spring inside the spool. So for one position we operate this solenoid, for second position we operate this solenoid. We will also see the close-up of these pictures. Now for this pneumatic cylinder, because the piston will be either fully extended or fully retracted, so to sense the two position we have two proximity sensors. These two are capacitive type proximity sensors. Now this sensor is connected to input port number 1 of the PLC here, somewhere here. The second one is connected to input port number 2 of the PLC. These solenoids are the outputs, so they are connected to the PLC on the output side. So you will see them when we have a close-up view of the PLC. Similarly, this is a single acting pneumatic actuator controlled by a 3x2 solenoid valve having one solenoid, again two proximity sensors. Then this is an AC induction motor, synchronous motor, which can rotate in clockwise and anti-clockwise direction. Similarly, this is also an identical AC synchronous motor which can rotate in clockwise and anti-clockwise direction. These are some more, these are proximity sensors and these are limit switches. So on this board, we have a total of 11 sensors, number 1, number 2, number 3, number 4, 5, 6, 7, 8, 9, 10 and 11. And we have a total of 7 outputs. Output number 1, output number 2, output number 3, then output number 4 for clockwise and output number 5 for anti-clockwise. Similarly, output number 6 for clockwise and output number 7 for anti-clockwise. Now this is a close-up of the PLC. So on this, what you see is that there is a display. Then there are 5 buttons here for programming. Now on this side, what you see is screw terminals for the input, and on this side we have screw terminals for the output. Now these screw terminals are covered by this connector. This connector basically connects this wire to the serial port of the computer so that we can make the ladder diagram in the computer and transfer it to the PLC. All these wires are of the sensors and the wires on this side are of the outputs. You may be able to see there are number beads on the wires which indicate that okay, which wire is coming from which sensor. And this PLC is an ABB make PLC, as you can see from here. Now this is a close-up view of the single acting pneumatic actuator. So here you can see that we are controlling this actuator with this valve. Now physically this is a 5x2 valve because there is a pressure port. This is the pressure port. This tube is coming from the compressor. Working port 1 connected to the cylinder. Working port 2 which is blocked by a plug. There is one exhaust port and there is second exhaust port. But we are using it as a 3x2. Reason being that this working port and this exhaust port are not being used. So we are basically using the pressure port, this working port and this exhaust port. Now this has a single solenoid and it also has a spring inside, like similar to the one you saw in the animation. Now when the solenoid is not energized, the spool position is such that the working port is connected to the exhaust port and the pressure port is blocked. Whereas when the this solenoid is energized, it moves the spool in such a way that this exhaust port is blocked and the pressure port is connected to working port. That is, then the piston will extend. Now the retracted position and the extended position are sensed by this sensor and this sensor respectively. This is connected to input number 3 of the PLC and this is connected to input number 4 of the PLC. This is the output number 3 of the PLC. So just remember input number 3, input number 4 and output number 3. Why? Because you will shortly see a video. Now before we see a video, what you see on the screen is a program of a PLC. It's a one-line program. We will be doing this programming in detail tomorrow, and programming is quite easier, and in one day only you will be able to grasp the fundamental of the ladder programming. So what you see in this diagram is 2 vertical lines and 1 horizontal line. Horizontal line has I4 symbol here and Q3 symbol here. Now it is 4 and I means input. Input 4 is, now we are referring to the this sensor input 4 and Q3 is referring to this coil. So what we are saying in this program is that when input number 4 senses something or input number 4 is closed, then output number 3 should be switched on. So let's see the video. So what you will see in the video is, let me move the video a little bit. So what you will see in the video is that when an object is brought in front of this proximity sensor, the piston will move forward. As long as the object is here, the piston will remain extended, but when the object is removed, the piston will move back. That is so because in the program we have said that when input number 4 is closed means it is working, then output number 3 should be switched on. So when an object comes in front of this sensor, the sensor will give a signal to the PLC. The PLC will then start this solenoid, due to which the pressurized air will flow into the cylinder and the piston will move forward. And all sensors normally have a visual indicator, kind of LEDs attached to them. So I hope that when this sensor works, when the pen will be brought in front of it, you should be able to see an LED glowing here. Now I will start the video. So now if we see that here we have made a small automation that when a sensor detects an object, the actuator works. This kind of scenario is encountered on normally conveyors, that as conveyors are moving on which the components are moving, when the component reaches a particular location where the sensor is mounted, a pneumatic cylinder will normally eject it and push the component into a bin or into a lorry or something. Now, we will not discuss programming here, but I'll just want to show you some more videos. Although we will see them tomorrow, but here, now this is a close-up view of the double-acting pneumatic actuator. Now, this is input number 1, this is input number 2, this is the directional control valve for this actuator, and this is the solenoid, that is output number 1, and second solenoid output number 2. So if we look at a program, what you see is that now this program has two lines. In the first line we are saying that when I1 is closed, Q1 should be switched on, and when I2 is closed, Q2 should be switched on. So looking at the system, now you can see when the piston is in this position, I1 will be closed. That means then we are asking the controller to start Q1. When that happens, pressurized air will flow to this side and the piston will move forward. Now when the piston moves forward, this will stop sending signal, this will become open, and when this reaches here, this will start sending signal to the controller, that is I2 will be closed. When I2 is closed, then as per the program, the controller will switch on Q2. When that happens, pressurized air will flow on this side, and then the piston will move backward. So when the piston moves backward, again this will switch on. So what will happen? The cylinder will keep on reciprocating. So let us see the video of this. So because of this program, the cylinder will simply keep on reciprocating between the two extremes. So what we see is that solenoids, which are electrical systems, they are actually moving, making the spool move inside the directional control valve, due to which the air flow is occurring in different directions. So electrical systems have a very important role to play as actuators in automation systems. Second thing is the PLC, which is an electronic component. So now it is the PLC in whose memory the program is running, and based on the program and the signals it receives from the sensors, it is actuating the electrical outputs. Now another question was that how timing can be done in DC valves. So as I said that we will discuss that in detail also, but today now let us see another system. Now here, this is the same system for which we saw the video right now, a double acting actuator controlled by 5x2 directional control valve, having reciprocating motion, but right now we are introducing a time delay. Look at this diagram, and if you recollect, the first line is same as in the previous program. Input I will result in switching on Q1. Second line, I2. Now here instead of Q2 we have a timer, and in the third line the timer is now activating Q2. So what we have done, we have inserted a timer between I2 and Q2. So what will be the effect? That when the piston is retracted, I1 is closed, immediately Q1 will be switched on and the piston will move forward. Now when the piston moves forward, I2 will be closed, but then what will happen? That event will trigger a timer. The timer, in the timer we have set some time, maybe 5 seconds, 10 seconds. So only after that time has elapsed, then only Q2 will be switched on. So let us see the video. Okay. So what we just saw was that incorporating a time delay in operating a cylinder. Now there is a very important point to be noticed here. In our previous example, the piston was reciprocating continuously, whereas in this example, the piston is reciprocating, but there is a time lag when it starts the backward journey. Now we have made changes to the behavior of the system or to the functionality of the system by simply changing the program. Right? So when we have a controller, then we have a flexible automation or a flexible system whose functionality can be changed by simply changing the program. We need not make changes to the hardware circuit. This thing will discuss in the afternoon session, that we'll elaborate on this. Now another feature which I will demonstrate just right now is, along with the time delay, counting. Because I said on a previous occasion that timers and counters are two very important components of automation as well as of PLCs. Again, our system is same. The same double acting cylinder, the same directional control valve, same sensors, same coils. But now the program has been further changed. We have I1, input sensor number 1, and Q1, coil number 1. Now we also have another component in the circuit, which is basically a counter. Then we have I2. I2 we are using to start the timer as well as to increment the counter. The last line remains same. The timer is actuating Q2. Now let us see the video. So here what you will see is that the piston will extend for a limited number of times, then it will come to a halt. So now the video is still running, but as you can see, the piston has now stopped. The reason being that a count value of 5 was given in this program to the controller, so that after making 5 strokes, the piston should stop. So this was a brief introduction about automation. The second major component of this course is robotics. So we will now have a brief introduction to robots. So again, I may not go through all the slides of this PPT because it's an introductory session. Now talking of robots, first of all, a very briefly historical perspective, the word robot was first used in 1921 by a Czechoslovakian playwright, Karel Čapek. He wrote a satirical drama, kind of a comedy, Rossum's Universal Robots. In this drama, the robots word was used for slave, or you can say forced labor. The word robota was derived from the Czechoslovakian language, which means slaves or forced laborers. Then the term robotics was coined by an American author and professor of biochemistry at Boston University, Isaac Asimov, in his short story titled Run Around. So here you can see that both the terms robot as well as robotics were coined not by engineers but by literary people. Now what we see here is a robot manipulator. So as we can see, we may state that industrial robot is a mechanical manipulator that can be programmed to perform a variety of tasks. So in this definition, it's not definition basically, it's a statement. There are two important things. One is a mechanical manipulator and second is which can be programmed. Now this is also a mechanical manipulator. This is also powered, but this is not programmable. So here this manipulator is moved by using joysticks, which the operator can move to move the manipulator. So if we come to the exact definitions of robots, there are two definitions. One is a definition from a dictionary, Webster dictionary, an automatic apparatus or device that performs functions ordinarily ascribed to humans or operates with what appears to be almost human intelligence. The second definition is more technical, given by Robotic Institute of America. It says a robot is a reprogrammable, multifunctional manipulator designed to move materials, parts, tools, or specialized devices through variable programmed motions for the performance of a variety of tasks. So robot configurations and kinematics will be discussed in detail, but let us quickly go through. There are mainly 4 robot configurations: Cartesian, cylindrical, spherical, and articulated. Now in all these 4 you can see we are talking of 3 degrees of freedom. In the first one, all 3 degrees of freedom are linear and right angle to each other. In cylindrical, two degrees of freedom are linear and 1 is rotational. In spherical, 1 is linear and 2 are rotational. And in articulated, all 3 are rotational. So normally a manipulator will have 3 degrees of freedom. In addition, the tool that is attached to the wrist will have additional degrees of freedom. So what we see here is a Cartesian robot. So as you can see, it's an industrial robot whose 3 principal axes of control are linear and are at right angles to each other. A popular application of this type of robot is a computer numerical control machine. So CNC itself is kind of a Cartesian robot. Otherwise, Cartesian robots are also very popular for placing things in and out of automated storage and retrieval systems. Then second is cylindrical robot. So here you can see there is one rotational degree of freedom and there are two linear degrees of freedom. So a horizontal arm is mounted on a vertical column and this column is then mounted on a rotating base. The horizontal arm can slide vertically on the columns. So we can see a video of this also. So you can see a linear motion, second linear motion, and then the rotational motion. So here you can see that for the motors are being used for all type of motions. For linear motion, lead screw mechanism is being used, and rotational is directly achieved through the rotation of the motor. Again, right. Now the next one is a spherical robot, also called a polar robot. So here, as you see in the diagram, there are two degrees of rotational motions and one linear. So a horizontal arm is mounted on a rotating base. The arm can also move through certain angle with base as the pivot. The horizontal arm can slide horizontally. So if we see the video of it, you can see there are again second rotational motion and a linear motion. Then before we come to the last one, that is the fully articulated, there is another configuration which is, although it is intermediate between these, but it is given special importance because of its usefulness. It is called SCARA, or Selective Compliant Assembly Robot Arm, or Selective Compliant Articulated Robot Arm. So in the figure, as you can see, there are two rotational motions and there is one linear motion. But these are slightly different as compared to what you saw earlier. Right? Here, both the rotational motions are in one plane only. There they were in the earlier one, the two rotational motions were in two perpendicular planes. So the arm is compliant in the XY direction but rigid in the Z direction, hence the term selective compliant. The jointed two-link arm layout is similar to human arms, hence the term articulated. And this feature allows the arm to extend into confined areas and then retract or fold up. Let us see a video of it. Let me play it by some other means. I'll just show you the video by opening it by some other means. So this is the video of a SCARA robot. As you can see, the two rotational DOFs are in the same plane. So what you just saw, that during this video, this robot had transferred 168 parts in 40.99 seconds. That is 0.244 seconds per part. And if we go slightly back in this video, so you can just see that on this pallet there were holes, the speed as well as the accuracy, because it was lifting the steel balls and placing them in different depressions. There were not holes, there were depressions made in this. So the speed and accuracy is marvelous. Okay, we go back to our presentation. Now, the last configuration of this in robotics is articulated robots. So as you can see in the diagram, all the three degrees of freedom are rotational: base, shoulder, and elbow. Right? All these three are rotational type. So an articulated robot consists of two shoulder joints. Two shoulder joint means, because this base and this, both these joints are considered as shoulder joints, one elbow joint, and two or three wrist joints. So these are the most common type of robots. So we can have a
industrial robots
video
have
of
various
this.
axis configurations. However, the vast majority of articulated robots feature 6 axes, also called 6 degrees of freedom. 6-axis robots allow for greater flexibility and can perform a wider variety of applications than robots with fewer axes. Axis 1. This axis, located at the robot base, allows the robot to rotate from left to right. This sweeping motion extends the work area to include the area to either side and behind the arm. This axis allows the robot to spin up to a full 180-degree range from the center point. Axis 2. This axis allows the lower arm of the robot to extend forward and backward. It is the axis powering the movement of the entire lower arm. Axis 3. The axis extends the robot's vertical reach. It allows the upper arm to raise and lower. On some articulated models, it allows the upper arm to reach behind the body, further expanding the work envelope. This axis gives the upper arm the better part accessibility. Axis 4. Working in conjunction with the axis 5, This axis aids in the positioning of the end effector and manipulation of the part. Known as the wrist roll, it rotates the upper arm in a circular motion, moving parts between horizontal to vertical orientations. Axis 5. This axis allows the wrist of the robot arm to tilt up and down. This axis is responsible for the pitch and yaw motion. The pitch or bend motion is up and down, much like opening and closing a box lid. Yaw moves left and right, like a door on hinges. Axis 6. This is the wrist of the robot arm. It is responsible for a twisting motion, allowing it to rotate freely in a circular motion, both to position end effectors and to manipulate parts. It is usually capable of more than a 360-degree rotation in either a clockwise or counterclockwise direction. The most popular 6-axis robots are manufactured by Motoman, Fanuc, Panasonic, ABB, and Nachi. To purchase a 6-axis robot, contact RobotWorks.
Okay. So these are the typical configurations of robots. Now, just like any automation system, a robot also has basic components. So the most basic is the manipulator. That is the mechanical linkage which actually does the work. So manipulator is series of rigid members called links connected by joints. Then we have actuators which will move this manipulator by moving the individual joints and links. So actuators provide power to the manipulator, and then we have sensory devices which will monitor position, speed, acceleration, torque, etc. Controller which will provide the intelligence to make the manipulator perform in a certain manner. And then drive circuits or power conversion units which will take signals from the controller and convert it into meaningful power level so that actuators can move. So what you see here is photograph of a robot in our laboratory. So this robot is a fully articulated 5 degree of freedom robot. So along with the robot, what you see is a teach pendant. We can control the robot by using the teach pendant. Then this is the controller of the robot and the computer system in which the robot software can be run. As you can see here, what you see here is the motors. So these all are motors which basically make the joints and the links to move in space. So when we give the command, when this controller gives the command to the motors to move at a certain speed through a certain angle, the motors will do so. The motors are provided with feedback systems through optical encoders. The encoders will then provide the feedback to the controller that the motor has moved through this much angle and at this much speed. The teach pendant can be used to manually move the robot or even to run programs which are previously made. Now this particular robot is a scorebot robot provided by a company named Intellitech, and these are in this figure you see the links and joints. So what you see in this figure are the links, base, body, then upper arm which is a link, forearm which is a link, and then the joints, the base joint, the shoulder joint, the elbow joint, and for the wrist, pitch and roll. Now in this particular robot, all the motors are mounted here at the base. So this is a close-up view. So here you can see 1, 2, 3, 4. 4 motors along with timing belts and pulley arrangements for operating different joints. Now all these motors are DC servo motors. So these motors, they have the motor as an encoder on one end to provide feedback of speed and position to the controller. Then there is a gear drive on the other end, and then these connectors that you see, these are for the power and these are for the encoder. Now, as I said, that along with the encoder there are cams and micro switches which are attached. We will discuss them in detail when we discuss robotics. So let us, for the time being, we will skip them for the time being. This also we will discuss in our session on robotics. Now, just a very brief introduction to it, robot programming, which will be basically we will see a video that how a robot works when programmed. Now let us see a robot program. Now this video is about a pick and place operation. The requirements are that a robot has to pick an object from one location and place it on another. Then another object will come at the initial location. The robot will move back, again pick the second object and place it at the target position. It's a cyclic operation, so which the robot will perform. Now for this, what are the requirements? One is that we must be able to tell the robot the positions from where the objects are to be picked and where the objects are to be placed. Now these are the minimum 2 positions. Otherwise, when a robot moves to pick an object, it should first move close to the object which is to be picked. Then there normally the robot will open its gripper and then move to the exact position where it can grasp the object. Similarly, after grasping the object, the robot must move slightly vertically up so that the object is clear of the surface on which the object was placed. And then the arm will move through the space, go to a position so that the object is as close to the surface where it is to be placed as possible. And then it should release the object very carefully. So a number of positions have to be first recorded and then they are put in the program. And the recording is done manually. The robot is moved manually through teach pendant and the positions are recorded. And then we must decide the speeds at which robot must move. So after recording positions and deciding the speeds, program is coded using relevant commands. Then the program is executed, resulting in the robot performing required operations. So today we will just see the video. This we will do later on. Now the video that you will see, it is for this robot and you can go through the program. This is the complete program. So we have recorded some positions which have been numbered as 1, 2, 3, 4, 5, etc. And as you can see in the first statement, go to position 1, speed 5. That means we are instructing the robot to go to position 1 with a speed code of 5. Now 5 here means a medium speed. Then in the second command we are asking the robot to open the gripper. Third command we are asking the robot to go to position 2 with speed 1, that is at a lower speed. Then wait for 3 seconds. Wait 30, 30 is basically here the unit is 1/10 of a second. Then close the gripper, then go to position 1 And then all the commands, as you will see, are basically to go to different positions at different speeds, waiting, opening gripper or closing gripper. So you will see the execution of these commands in the video. So this is position 1 and this is position 5. Sorry, this is position 2, I'm sorry, this is 5. So this is position 1, open gripper, position 2, close gripper, move back to position 1, then go to position 3, then position 4 and then release the object. So here we are placing the same object back to its original location so that it can perform the operation in cycles. So that was all about the introductory session on automation and robotics. So now I will invite questions, any queries from the centers and from the participants in the studio. So first we can go to the centers one by one and ask if there is any query. This is, I think, Punjab. Okay, this is Gyan Jyoti. This is Hoshiarpur. This is Gyan Jyoti. Right. Okay, Gyan Jyoti. If there is any query, we have just gone through a introductory session on robotics and automation.
Yes, sir.
Yeah, Dr. Neeraj, yes.
So Sharad. So I have one question. How the motion or how the speed is decided based upon the inertia? Speed of a robot is decided based upon inertia. Distance is one thing. I have one query related to inertia. How it is decided based on inertia, speed, that is.
You see, basically, because here we are talking of control, because when we are going to position the rest of the robot at a particular location, the first thing is that a robot arm has its own mass, hence inertia, its own damping and stiffness. So the for deciding the speeds, what is also called as trajectory planning, where the path and the speed, everything has to be decided. So modeling is required. So for a very accurate application, we need to have a model of a robot, so we can do the modeling and accordingly decide what should be the speed. Because if we, from mechanical point of view, if we talk of a equation relating the inertia, damping and stiffness of a system to the force input, then we know that there we can have under damped system, over damped system, critically damped systems. So accordingly, overall a model of the system is of the robot is required. The load it has to carry, the model of that load is required, because the load may be fixed. For example, a very simple load, like in this video you saw, it is only picking up a very small block, but this load can be a difficult load also. For example, a ladle containing molten metal, right? So there again, because it's a liquid, so more complexity comes into play. So essentially I will say we need to have a very good model of the system based on which we can decide that okay, what should be the speed.
Right, sir.
Okay, thank you. So Punjab University Regional Center Hoshiarpur, any query? Yes, Dr. Saab, boliye.
No, sir, thank you. I just
Oh,
came up here to unmute the button, so
okay,
that
okay.
you feel like we are also responding.
Okay, right. Okay,
Thank you.
thank you. Next center. Now, Gandhi Academy of Technology and Engineering. I think, sir, your mic is mute. Please. Sir, your mic is mute. We cannot listen to you.
Hello.
Now it is okay. Yes. Hello.
Yes, sir. When programming an object, जो object का जो weight है ना, weight you have to feeding the program.
Yeah, the weight of the object is?
सर object का जो weight है,
Yes.
weight lift करने के लिए जो robot को have to feed the program. Variable weight है ना, weight मतलब 5 kg और 10 kg 15 kg डिफरेंट टाइप्स ऑफ लोड ऑब्जेक्ट है वेट का ऑब्जेक्ट है तो वी हैव टू लिफ्ट तो वी हैव टू फीड द प्रोग्राम टू रिप्लेस द डिफरेंट टाइप्स ऑफ वेट
Yes. Well, there are two things. There was a similar question from another center regarding inertia. That basically is concerned with the mass, and that's basically concerned with the weight. So as I said that for deciding the accurate speeds and accurate positioning, we need a model of the system. So through modeling, we can decide, okay, what speed should we keep so that we can achieve required accuracy and positioning, accuracy in positioning. So is your question the same about that or something else? Because here the voice was not very clear. That is why I was able to understand that your question was about weight that the robot has to carry. So that's
weight
yeah, weight. That's what my answer is. That based upon the weight, we have to decide the speeds. Right. So for that, we need a modeling.
okay thank you sir
Okay, welcome. Now from Tamil Nadu. Any question?
Sensor or any other image processing or something?
So please, you can ask some question if you have.
Sir, how the object can be detected, sir?
How the
object? What object you want to pick up? So
okay.
how?
You see, in this video, we did not talk about detecting the object. Otherwise, objects can be detected by various ways. We can have proximity sensors, or there may be a weight sensor on the platform on when the object is being kept. Or object can also be detected through cameras and image processing. Object's shape, object's color, object's orientation, everything can be detected through image processing by capturing the visual through a camera and then processing the image. So that can be done.
Yes, sir. Okay, sir. Thank you.
Thank you. Okay, so any questions from the participants in the studio? Yeah, you see, gripping power is actually it again. It requires depends upon the weight. Number one. Okay. Number two, if the object is delicate, then we all, along with the gripping power, we have to decide how much pressure to apply. Okay. So for that, there are tactile sensors or pressure sensors. So with the when the robot gripper, when it grips the object, a feedback is given to the controller that how much force is being applied by the gripper. So in the logic, there is a limit is set that okay, if it is very delicate object, then it has to be handled like this. Okay, na? So then we may try to achieve greater friction between the gripper and the object by some other means. Or if we are handling, for example, if we are handling say some sheets, if the sheets are magnetic, then we can have a magnetic type of gripper. For things like glass, etc., normally vacuum grippers are used. So on a flat surface, vacuum grippers can be used. Okay, so after the questions, now it is 12:45. Now we'll break for the lunch, and we will meet again at 2 o'clock after the lunch for our next session. In our next session, it's going to be a very important session because there we will discuss that how do we make programs based upon a given problem. So please be here in time at 2 o'clock. Thank you so much.
तो उससे ना कंट्रोल ही नहीं हो रहा है।
So we'll be starting shortly in 2 minutes as all the centers join. आ गए सारे सेंटर? चलो, कौन सा नहीं आया? कौन से वाला? तमिलनाडु वाला? चलो कोई। Okay, good afternoon. So let us start with our afternoon session on digital logic and logic circuits. In this session, we learn how to basically make logic for digital problems. Consider the example of automatic sliding doors. So in automatic sliding doors, what we have is we have door panels and sliding mechanisms. So door panel are the actual doors which will slide so as to open the way or to block the way. Sliding mechanisms are which will make the doors actually slide, open and close. Since the fundamental problem is to move the doors, so obviously the first thing that we need is actuator. So in this picture, as you see, what we see is a DC brushless motor. Then we need some control system to do the operation. So a control module is shown here. Then is the function linking PCB, so a printed circuit board for auxiliary functioning. Then this is the hardware, which consists of brackets for attaching the doors, and of course the belt and pulley arrangement as you see here, which will slide the doors so as to open them or close them. Now if we see the general sliding mechanism components, we'll have an actuator, a motor, then a transformer for converting AC to DC, etc. Then a controller, then hardware like return pulleys and brackets. This is shown as the timing belt, tooth belt. And then primarily we need some kind of sensors. For example, the sensors shown here are microwave sensors. So we may have microwave, infrared, any type of sensors. So now how to connect the sensors and actuators in a circuit. Now when we have a controller in a circuit, it's fairly easy to connect the sensors and actuators. You simply connect all the sensors to the controller on one side, on the input side, and all the actuators to the controller on the output side. We need not be worried about that about their arrangement. The rest of the work will be done by the logic. But the main thing is how to make the logic. So we'll do that by taking the example of you can say a PLC, although logic is general in nature and it can be implemented in any type of controller. Now, before we go to the next slides, I will now go to the board and we will discuss the problems of formulating logic. So we'll just adjust the camera. Focus शायद भी ज़ी करनी है. थोड़ा सा और छोटा कर. Okay. Now as we started with the problem of sliding door mechanism. So with any mechanism we have an actuator. Here also we have an actuator which is a motor. So let us say that this is a room. And this is a room and we need sliding doors to be mounted here. Now, as we saw that for moving the door, we need a motor and sensors. Now, in case a person approaches the door from outside, then we need a sensor outside. And if the person approaches the door from inside, then we need a sensor on the inside. So participants in the studio, you can turn your faces to this side, easier for you. And then we will have a motor which will operate the door. So this symbol is.
Excuse me.
Yes, please.
Excuse me.
Yes, please. Yes, please.
Sir, is it not audible, sir? This is not audible, please.
Okay. So I think we'll have to move the mic or we can just.
Your system is not clear to move.
Also, please let me know about the video. In the video here, like whatever I'm writing on the board, is that clear?
So you have to sound your mic.
Please let me know the diagram that I'm drawing on the board. Is that clear? Mic is bar. The wire length is limited. पूरी तो खींचेगी ये वाली वायर है और आ जाएगा ओके Okay, so this is a motor, right? Now I will make another figure. Say this is the motor, and we know to operate a motor we need a circuit. So this is a simplest possible circuit to run a motor having a power supply and a switch. So remember, we are starting our discussion in which controller will not be a part of, but slowly we will converge on to that what are the advantages of including a controller. Now it is very obvious that if we close the switch, the motor will work, and if we open the switch, the motor will stop. So let us assume that there is a, instead of a sensor, there is a manual switch outside, and similarly a manual switch inside. So a person can come, press the switch, the motor will work, the door will open, the person will pass through, and let us assume that after that springs will bring the door back into closed position. So this is a switch. Now this switch may be outside. Similarly, because we need two switches, one for outside, one for inside. So we have to place the second switch also in the circuit. Now by inspection only, here we see that if this switch is closed, let us say this is the outside switch. So if this switch is closed, the motor will work, and when the switch is open, the motor will stop working. Now by inspection, we can find out that how do we place the other switch also in the circuit, so that if we operate either of the switches, the motor will work. So what we have done, we have placed two switches in in parallel. Now if somebody closes this switch, if this switch is closed, the circuit will be complete here and the motor will work. Whereas if somebody closes this switch, then also the circuit will be complete and the motor will work. So for such a simple arrangement, merely by inspection we can come to know how do we make a logic circuit. Similarly, if I make another diagram, all of us can very easily see that how will the system work. The motor will work only when both the switches are closed, because then only the circuit will be complete. So one switch may be a supervisor switch and one may be an operator switch. So that When the operator closes the switch, the system will work only and only if the supervisor has also given a green signal. Otherwise, the circuit will not work. Now, if we look at these two diagrams and observe their functioning, they are working on two very standard logics. OR logic and logic. Now, a very important step in formulating digital logic is to make truth tables. In truth tables, what we do is we make a table of inputs and outputs. For example, here, if we call this input as A and this, the second input as B, and the output as P, then for this circuit, the truth table can be made correlating P, the state of P to the states of A and B. Again, for making truth tables, we make use of binary numbers or bits. Binary digits, that is 0 and 1. So if we assume that when the switch is open, we will denote it by the binary digit 0, and if the switch is closed, we will denote it with binary digit 1. Then we can represent the different possible states of the A and B switches. Similarly, when either of the switch is closed and the motor is working, so for the motor to be in working condition, we will use 1, and when the motor is not working, we will use 0. So one possibility is that both the switches are open. When both are open, the motor will not work. Now, let us say switch B is closed and switch A is open. So switch B is closed and switch A is open. Now, since the circuit is complete through this path, so therefore the motor will work. Another possibility is that switch B is open and switch A is closed. So switch B is open and switch A is closed. Now the circuit is complete through this path. So now also the motor will work. The fourth possibility is that both the switches A and B are closed. Now again, because the circuit is complete, the motor will operate. There is no more possibility. So here we had two inputs. Both the inputs are binary. Therefore, the number of possible combinations are 2 raised to the power n, where n is number of inputs. So these 4 combinations were possible. Now, if we look at the adjoining circuit, since here are also two inputs, that means therefore possible combinations are same, that is 4, and the combinations will also be same. Either both are open, or B is closed, or A is closed, or both A and B are closed. Now looking at this circuit, we can very easily see that if both the switches are open, the motor will not work. If B is closed and A is open, that is this state, then also the circuit is incomplete and the motor will not work. When A is closed but B is open, then also the circuit is incomplete and the motor will not work. Only when both A and B are closed, then only the circuit is complete and the motor will work. So we have a truth table for this circuit as well as for this circuit. Now for this particular problem, what we did was we just made this circuit by inspection, and from that we made the truth table. And here we just made another circuit, and from the circuit we made the truth table. Actually, the process is reverse. We first make the truth table, and then from there we derive the logic circuit. Now I will go to the laptop and just write the steps in Word, 4-5 steps, that how do we make the logic, and then we'll again come back to the board. So normally what we will have is we are given a problem for which we have to make the circuit. So how do we make the circuits? I will just write 3-4 steps for that, and then we will go back to the board. Step 1, we identify inputs and outputs. I will just reduce the font size so that we can have, because I think it's quite visible. This is okay. Now, from the problem statement, we will know that how should inputs and outputs interact. So after identifying inputs and outputs, we will make truth table. Then from the truth table, we will formulate Boolean expression then we will simplify Boolean expression by using Boolean algebra, and then from the simplified Boolean expression we will formulate the logic circuit. Right. So first step is to identify inputs and outputs. Second step is to make truth table. Third step is to formulate Boolean expression from truth table. I should write here. And next step is to simplify the Boolean expression by using Boolean algebra. And from there we can formulate the circuit, the logic circuit. Now let us implement these 4 steps by using an example. So we'll again go to the board. So these 2 diagrams of the truth tables I am going to erase. Now let us write a problem statement using this room only. Now let us say that what we want is that if a person comes from outside, presses the door should open, but simultaneously if a person has pressed the door from inside, then the switch from inside, then the door should not open. So I will repeat the problem. A person comes from outside, presses the switch and the door opens. He goes into the room, the door closes. A person comes from inside, presses the switch, the door opens. Then he passes through the door again closes. Now in case 2 persons approach the door, one from outside, one from inside, and they simultaneously press the switches, then the door should not open. Why? Because there is a danger of the people striking each other. Now that is the problem statement. Now from this problem statement, our first step is to rectify inputs and outputs. We already have the inputs and outputs identified here. There is one switch outside and one switch inside. So these are 2 inputs and a motor to open the door, that is the output actuator. So again, let us say the outside switch is A, the inside switch is B, and the motor is Q or B, whatever. So we have first step to identify inputs and output that we have done. So the first step is identifying inputs and outputs. So we have 2 inputs and 1 output. Second is to make truth table. Now from our past two examples, we know that for two inputs we have four possible combinations. There is nobody present outside, nobody present inside, motor does not work. A person presses the switch from inside, but nobody has pressed the switch outside the room, so the door opens. Third possibility is a person has pressed the switch from outside, nobody has done it from inside, the door should open. Now two people come and simultaneously press the switches. So we want that door should not open. So that is the truth table. Now after writing the truth table, now our next step is to formulate the Boolean expression. Again, there are steps of formulating Boolean expression, and there are different methods also. The method which I will be demonstrating here is called sum of products. So there are different methods. I am going to follow the method sum of products. Now in this method, what we do is we focus our attention to those rows where the output is 1. Because the logic is meant to operate the output. So in this we have these two rows where the output is 1 and the output is 0 in the other two rows. Now in this row, you can say this is the second row basically. It is the first row, second row, third row and fourth row. Now for each of the second and third rows, we will write the expression for Q is equal to A into B. So for row number 2, if we write the expression Q is equal to A dot B or A dot B, now here A is 0, B is 1, so 0 into 1 will be 0, whereas actually the Q is 1. So what we will do, we will modify this expression and write it as A complement into B. Now we know that we are dealing with binary digits. Which can have a value of either 0 or 1. So if we have a binary digit, say C, which is 0, then the complement of C is 1. Similarly, if we have a binary digit D, which is 1, then the complement of D is 0. So when we write complement of a binary digit, we are basically writing 1 in place of 0 or 0 in place of 1. So here, since A was 0, so A complement is 1. So 1 into 1 is equal to 1. Now we will apply the same technique to row number 3. in row number 3, A is 1, whereas B is 0. So we took B complement so that it is 1 into 1, that is 1. Now after writing the output as the product of inputs, then we are going to take its sum. So we will say that combining them, Q is so this is the sum of products method. So the third step is so that is what we have just done. We have formulated the Boolean expression as this. Fourth step is simplify Boolean expression, which in this case is not possible because remember we are talking of algebra, Boolean algebra. So like in algebra you can take some common terms. So similarly here also you can take common terms, but in both these terms there is no common term. Here we have A bar dot B, here we have A dot B bar. So neither A is common nor A bar is common. Similarly, neither B is common nor B bar is common. So this step will not apply to this example. Now we will return back to this, but please let us go back to our presentation and we'll again come back here. Right. So if there are any questions, we will take it after we go through our presentation. Okay. So we started with the example of a sliding door. So next we see a number system. Right. The number system that we use in our daily lives is decimal system. It has a base 10. Why? Because we use 10 digits 0 through 9. So I will say we use symbols 0 to 9, that is 10 symbols we use. So that is why we say that the base is 10. In binary system that we were discussing on the board, the base is 2. Why? Because only two symbols are used, 0 and 1. Similarly, there are many more systems, hexadecimal, octal system. So just as an example, I am writing here hexadecimal. Right? Hexa means 6. We have hexagon of 6 sides. Decimal means 10. So total of 16 symbols. So the base is 16. And the symbols are 0 to 9 and then A to F. So binary number system is used to represent and manipulate numbers with digital devices. The reason for this is that the operation of digital devices is based on transistors that switch between two states, on and off states. These states may be designated by the symbols 1 and 0 in the base 2 system. Boolean algebra is an algebra that deals with binary variables and logic operations. The three basic logic operations are AND, OR, NOT, or complement. Right? And OR we saw in our two circuit diagrams, and NOT complement we used in our third example. A Boolean function can be either 1 or 0. Now, this is some basic Boolean theorems where x is a binary variable. For example, we are saying x dot 0 is equal to 0. Now, one thing more, when we say dot or product, we are talking of AND logic. When we say plus, we are talking of OR logic. So product implies AND, plus implies OR. So here we are saying x and 0 is equal to 0. Now since x is a binary variable, it may be 0, it may be 1. If it is 0, then we are saying 0 and 0 is equal to 0. If it is 1, we are saying 1 and 0 is equal to 0. That is what we saw in our AND truth table for the AND circuit. Similarly, x and 1 will be equal to x. For example, if x is 0, 0 and 1 is 0. If x is 1, 1 and 1 is 1. X and x is x. That is also true. 0 and 0 is 0. 1 and 1 is 1. X and x complement is 0. If x is 0, then this becomes 1. So 0 and 1 is 0. Similarly, 1 and 0 is 0. Now we come to OR. We say x or 0 is equal to x. If x is 0, then 0 or 0 is 0. If x is 1, then 1 or 0 is 1. Similarly, 1 plus 1 is 1, but 0 plus 1 is also 1. We saw in the OR circuit. 0 or 0 is 0, 1 or 1 is 1, that also we saw. Similarly, 0 or 1 will always be 1, 1 or 0 will always be 1. So if x is 0, then actually here it is double complement. It may not be visible, but it is a double complement. So that is complement of complement. So if x is 0, its complement is 1, and further the complement of 1 is 0. So therefore, x double complement is equal to x. Now these are some more Boolean expressions, Boolean algebra. X dot y is equal to y dot x. Commutative law. The same holds true in our day-to-day algebra also. Similarly, x plus y is equal to y plus x. So where x and y both are Boolean variables or binary variables having value of either 0 or 1. X into yz is equal to xy into z. X plus y plus z, where y plus z are bracketed, is equal to x plus y bracketed plus z. Associative law. X and y or z is equal to x and y or x and z. Similarly, x or y and w or z is equal to this. Distributive law, same as in our day-to-day life algebra. Now these are some consensus theorems which are very useful actually. So it says x plus x bar y is equal to x plus y. Similarly, x bar plus xy is equal to x bar plus y. X plus x bar y bar is equal to x plus y bar. X bar plus xy bar is equal to x bar plus y bar. And these are De Morgan's theorems which says that complement of x and y is equal to complement of x plus complement of y. Similarly, complement of x or y is complement of x and complement of y. Now these expressions are very important when we are deriving logic circuits from given statements. So digital logic is the word digital implies that the information is represented by variables that take a limited number of discrete values. Binary variables are also digital because they only take two values. Computers and microprocessor controlled systems involve digital signals with two possible signal levels. The two levels high and low are represented by binary digits 1 and 0. Now let us come to logic gates. We have just seen some logic gates. So these are the basic building blocks for digital electronic circuits. First of all, let us see AND. So we have just seen that if we have two inputs A, B, then the output A and B is given by this relation. And in our first example, we formulated this truth table from the physical layout of the circuit. Whereas on the left hand side, what you see is an AND symbol for this. There is a link also. We'll link about. Okay, that is just not required right now. Okay, then next is OR. A, B are two inputs and output is A or B. So this truth table we also formulated from our circuit, from the physical circuit that we had made. And this is the symbol for the OR gate or OR logic. Then NOT. NOT is complement. So what we say is if the input is 0, then its output is 1. If the input is 1, then output is 0. So after we go through these tables, we will make physical circuits for them showing that how do they actually relate with the real life. Not AND. Now, if you remember that for two inputs A, B, the AND is 0, 0, 0, 1. Right. So where whereas NAND is not of AND. To just so if we have an input A, B, then A and B is what we just saw. And this is the output of A, B. Whereas when we say NAND, we basically mean not AND. Right. Or you can say complement of AND. So what is the complement of 0? It is 1. Complement of 0, 1. Complement of 0, 1. Complement of 1, 0. Right. So that's what we were seeing in the NAND. the complement of AND. Similarly, this is complement of OR, not OR, that is NOR. Right. So whereas for A, B, OR will be 0, 1, 1, 1, NOR will be 1, 0, 0, 0. And you also look at the symbols. This is the symbol for the OR gate, and if we put a small circle here, it becomes not of or NOR. Similarly, if we go to the previous slide, this is the symbol of AND, this is the symbol of NOT. Then this is exclusive OR XOR, what is called. Now if you look at this truth table is same as we just formulated for our problem, that when you want to open the door, only when one switch is operated. If both the switches are operated, the door should not open. So this is the same truth table that we just formulated, so it is XOR. Okay, then we need not do this. So this we have already basically, these are different truth tables. You can just take 2 minutes and go through the truth tables, then I will resume. Here A and B are inputs and C is the output. एक फोन जरूरी है. Okay, so now we have, okay, so before we go to some videos, so what is shown here is basically a NAND IC, just an example taken from internet, that for making you can say electronic logic circuits, we have different kinds of ICs available which contain the different type of logics. This is an example of an NAND IC, sorry. Now we come to logic circuits, but before we come to logic circuits, let us see some videos for AND, OR, NOT, NAND, NOR, XOR. Now it is the same PLC that you saw in the morning. So again, we will only see the videos. The logic we will discuss tomorrow, how it was formulated. So here we are seeing the videos to emphasize that actually when we say and, or, X, or, not, what do we mean by that? So here the problem is, statement is, a motor runs, when two contacts are closed and stops when either or both contacts are opened. So we just made a diagram on the board also, but here we are so if you look at this program for this logic, you will see it is similar to the kind of diagrams I made on the board. For example, if this is one switch I8, second switch I9, and the motor Q6, so if we close the circuit like this, that is, you have a power supply here which is, we can say, not shown, then this will make a complete circuit, and when both I8 and I9 are closed, then only the motor will run. Now before we run the video, let us identify, as I discussed in the morning, this is input number 8, this is input number 9, and this is our output motor Q6. Now this switch and this switch both are attached to the PLC on the input side, and the motor is also attached to the PLC on the output side. Let us see the video. So there are two switches, I8 and I9. So only when both are pressed, then only the motor will work. So this was AND logic. Now let us see OR logic. A motor runs when either or both contacts are closed and stops when both contacts are opened. Now it is the same I8, I9 and same output, but now the logic is different. And again, if I say that there is a power supply here, then you will see that this diagram is similar to the kind of diagram we made on the board. Press I8, release I8, press I9, release I9, press 4. Release 4. Not logic. A motor which is running stops while a contact is closed. So in this, a switch I8 and an output Q6, you will see in the video. So this is I8 and this is Q6. So when the video runs, this motor will rotate, and when I8 is closed, then only the motor will stop. Otherwise the motor will run. So it is now not logic or complement. Now the motor is running. When I8 is pressed, the motor stops. When it is released, it runs. So now here we are talking of complement. So this we will see tomorrow. Now this is NOR. This also we'll see tomorrow. Now let us see this XOR, right, which we just formulated, which is exclusive OR logic. A motor runs only when either of two contacts is closed. Now here, when either I8 or I9 is closed, then only the motor will run. When both are open, the motor will not run. Also, when both are closed, then also motor will not run. So that is the logic. Let's just see the video. Right, so here we demonstrated the AND logic, the OR logic, the NOT or the complement, and exclusive OR, that is XOR. Now we'll talk of logic circuits. First of all, let us go through some problems. For example, it says, design a start circuit for a semi-automated punching machine with three variables as control parameters. The three variables are protective guard signal A, remote start signal B, and normal start signal C. The truth table for implementation is given. So here, in fact, rather than giving the problem statement, the inputs are given and directly the truth table is given. Right. We'll come back to this problem. Let us see another problem. An industrial furnace is to be controlled as follows. The contacts of a bimetallic strip inside the furnace close if the temperature falls below the set point and open when the temperature is above the set point. The contacts regulate a control relay which turns on and off the heating elements of the furnace. If the door to the furnace is opened, the heating elements are temporarily turned off until the door is closed. Specify the inputs and output variables for the system operation. Write the Boolean expression for the operation. So if we look at this problem, so from here we have to identify what are the inputs and what are the outputs. So I'll just give the participants in the studio and at the remote centers to try to list the inputs and outputs. Then after 2 minutes, then I will interject and we will discuss. So participants at the remote centers and in the studio, they can try to write on their notepads that in this problem, what are the inputs and what are the outputs. So, okay, if we discuss this problem, right, uh, actually there is one more step that you can add to the steps which I had discussed about formulating Boolean expressions. And that one step is you can make a rough sketch of the system, because that also gives us a good idea about the different components. For example, here we are talking of a furnace. The first line is an industrial furnace is to be controlled, right? Now the contacts of a bimetallic strip inside the furnace close if the temperature falls below set point. So that means the sensor is basically a bimetallic strip, the kind of strip which we have in our household irons. So they close if the temperature falls below the set point and open when the temperature is above the set point. So there is a circuit consisting of these bimetallic strips. Now what does this circuit further consist of? It says the contacts regulate a control relay. That means there is a relay which is being operated by these bimetallic strips, which turns on and off the heating elements of the furnace. And then further that control relay operates the heating elements of the furnace. Further it says if the heat door to the furnace is open, the heating elements are temporarily turned off until the door is closed. So if we say make a circuit of this, try to make a circuit of this. So I think I'll again have to go to the board. So we'll discuss this problem in detail. So first of all, let us say that we have a furnace, and naturally in the furnace what we need is a heating element. And what the heating element needs is a power supply. Now to open and close, to start or stop the heating, what we need is a switch. Now here this switch is a control relay basically. This switch is a control relay. Now this relay is either opened or closed depending upon the states of the bimetallic strip or by the doors of the furnace. So inside the furnace, the sensor is a bimetallic strip power supply. So this I have shown as a power supply. Now this bimetallic strip is sensing the temperature. If the temperature is below the set point, the strip is like this. And if the temperature is above the set point, then because bimetallic strips have different materials with different coefficient of expansion, so what happens, they distort. So when they distort, the circuit is opened. So that means when the temperature is high, the bimetallic strip will distort and this circuit will open. When this circuit open, the input to the control relay is removed, and the control relay will also break this circuit, and the heating element will be switched off. So as the heating element is switched off, the temperature in the furnace will come down. So when the temperature in the furnace comes down, this bimetallic strip will again become straight, and as it becomes straight, the secondary circuit will again be established. When that happens, this control relay is switched on. When this is switched on, the heating element will also start giving the heat. Now, apart from a bimetallic strip to sense the temperature in the furnace, there is another thing, the doors to the furnace are opened or closed. So that is also detected by some switch. There is a switch which is detecting whether the doors are open or closed. It may be some kind of a mechanical switch which remain closed when the doors are closed, but if the doors are open, this switch also opens. Now, since these two inputs are in series, the switch and the bimetallic strip, that means for the heating element to be on, the control relay has to be working. For the control relay to be working, this circuit should be complete. So that means the bimetallic strip should be touching the contacts as well as this switch should be closed. So from this sketch, we can easily sense that there are two inputs, a bimetallic strip and a mechanical switch maybe to sense the door status. And of course, the output here is the control relay. Let's call it Q. So we have identified the inputs and outputs. Now we have to make truth table. There are two inputs, both are binary. This is either closed or opened. Similarly, this is also either closed or opened. So both A and B are binary. So their possible states are now you can easily see that only when both of them are closed, then only the coil will be heating. So the truth table will be like this, exactly an AND logic. And from here we have to formulate a Boolean expression. Although it is fairly simple, but let us just revise the steps. So for formulating Boolean expression, we have to focus on only those rows where output is 1, which in this case is row number 4. And here Q will be A into B. So this is our Boolean expression, and obviously we cannot simplify it, so we cannot simplify the expression. So for this given problem, we have identified the inputs and outputs, and we have formulated the Boolean expression. So now we'll go back to our next our presentation PPT. So next we discuss the another problem which is the last for today's session. It says consider a chemical tank for which three variables level, pressure and temperature are to be monitored. Design a circuit for sounding an alarm if any of the following combinations occurs. First combination is liquid level is low and pressure is high. Second is liquid level is high and temperature is high. Third is high liquid level with low temperature and high pressure. Right. Now, because we'll have to do it on the board, so I request the participants that if they can note down this problem, so after 2 minutes, so in 2 minutes you can note down the problem. It's a very small one. So after 2 minutes, we'll go to the board and solve this problem. Okay, then we'll discuss the problem on the board. And so, from this problem statement, we can see that we are going to measure three variables: level, pressure, and temperature. So, say there are three sensors, one for level, one for pressure, and one for temperature. So, when we identify the inputs, we say we have three sensors and we name the inputs as L, P, T. And output is an alarm. It says design a circuit for sounding an alarm. So an alarm is a output. We call it Q. Now in the second step we have to make truth table. So depending upon the states of level, pressure and temperature sensors, the alarm should work. Now we just discussed that the number of possible combinations of binary variables, they depend upon the how many binary variables are there. Where small n is the number of variables. So these are the possible number of combinations 2 raised to the power n. Now here small n is equal to 3 because there are 3 input variables L, P and T. So accordingly here we have possible 8 combinations. But remember we are interested in only those combinations for which output is 1. So rather than writing all the possible combinations, we will read the conditions for which the alarm has to be sounded and accordingly we will make the truth table. The first condition is liquid level is low and pressure is high. So let us make a decision that we will denote low value with a 0 and high value with a 1. So when the liquid level is low and pressure is high, the alarm should sound. Now this condition does not talk about temperature. Temperature may be low or temperature may be high. In both conditions the alarm should work. So in case the temperature is low, then this becomes 0, 1, 0 and 1. However, for the same condition, that is low level and high pressure, if the temperature is high, then also we need to sound the alarm. Second is level is high and temperature is high. Level is high and temperature is high, then alarm should work. Here this second condition does not talk about the pressure. So maybe the pressure is low or pressure is high, alarm should work. The third condition says high liquid level, low temperature and high pressure. So here the third condition specifies all the 3 variable states. High liquid level, so L is 1, low temperature T is 0 and high pressure. So this condition says that alarm should work. Now, as per the given conditions, we have formulated the truth table. Now, our next step is to formulate the Boolean expression. For the first row, Q will be equal to L bar or L complement into P into T complement. So wherever we have a 0 occurring, we are taking a complement of that so that all the terms are 1, 1, 1. For the second row, Q will be L complement into P into T. For the third row, Q will be L dot P complement dot T. For the fourth row, it will be Q equal to L dot P dot T. L dot P dot T complement. So the combined Boolean expression will be sum of all these terms. Now for this particular problem, we will have to go to the fourth step, that is simplify Boolean expression. Now how we will simplify it? So we have to take some common terms. For example, if we look at the first two terms, here L complement and P are common. Similarly, if you look at third and fourth, then L dot T are common. Then last we will write as such. Now from our slides on Boolean algebra, remember x bar plus x is always equal to 1. X plus x bar or x bar plus x is also always equal to 1. So this will be always equal to 1. Similarly, P bar plus P will always be equal to 1. Now, if there is any further common term, you can take it, it helps you. Again, from Boolean expression x plus 1 or 1 plus x, we should remember it is always equal to 1. So we have simplified the Boolean expression to this. Now there is no common term that we can take. Now I arrived at this Boolean expression because I combined first two, then next two. So if somebody does it by using different combinations, this may turn out to be somewhat different also, but there is nothing wrong in that. Now, one more thing that we should remember, and we can even recollect from our first two examples, that when switches are in series, the truth table is that of AND. Similarly, when the switches are in parallel, the truth table is that of OR. Further, we say that AND we represent by a product and OR we represent by a plus sign. So, for this, what we have is, we have two inputs connected by dot. That means L complement and P should be in series when we are talking of a logic diagram. Similarly, L and T should be in series in the logic. Whereas this term and this term, it should be parallel to each other. Now we can represent this in many ways. For example, if we represent it using the symbols that you saw in the AND or truth tables in electronic symbols, then we may say L, P, T. L complement. So this is the symbol of complement. So that means this is L bar. Now L bar and P, they are to be in AND. Similarly, L and T are to be in OR. In AND. These two are to be connected by an OR. So in terms of logic gate symbols, the logic diagram is this. Whereas in terms of PLC or ladder, then we can also use the same technique to formulate a ladder diagram. So that we will do when we discuss the PLC programming tomorrow. So I hope that the example that we have discussed today, you please remember, and because tomorrow we will use the same examples to learn how to program PLCs for these kind of things. And when we program, we will also see them in action using a simulator of the PLC. Now we'll stop here. So if there is any question from the centers or from the participants in the studio, you can ask. So I'll request the centers one by one. Gyan Jyoti, if there is any question.
No sir, no question from our side.
Thank you. Then Punjab University Regional Center Sharpur.
Yes, sir, I have question.
Yeah.
Through KMAP, I am getting the output P plus LP. So,
Pardon?
through KMAP, Carnomap, if we
Yeah,
sort
yeah,
of,
yeah. Yeah, that's what I said. That by either you are using Karnaugh maps or you are using sum of products or product of sums or whatever, right? So number one is you arrive at a Boolean expression, and when you simplify it, even during simplification, if two people combine different terms, the net final expression may differ.
but sir,
But the
number of gates increases
yeah,
there.
yeah, that's right. So it comes to efficiency, right? So that which one is the most efficient?
Yes.
Say, because in that case, if we can reduce the number of gates to minimum, that is always good, right? That is always good, even whether it is a hardware wise or whether we are doing a PLC program. There also, naturally, if we are simplifying the logic, it is always good.
Thank you.
Yeah. ये कौन सा है? तमिलनाडु. Okay, so we have a center from Tamil Nadu. If there are any questions, कॉलेज का नाम क्या है? SCS लिखा हुआ है मैंने कहीं. SCS. Okay. SCS VMV University है ना? SCS VMV University. If there is any question, SCS VMV University. SCS VMV University. If there is any question, you may ask. Please switch on your mic. I think your mic is mute in the software. Probably your mic is mute. Now you can speak. I think now we can hear you.
No question, sir.
Okay, madam. Thank you. Then we have gate. Isn't it okay? Okay. So any questions from the participants in the studio? Then we'll stop.
So we can get it on mistake in simplifying the next question.
Maybe. Right.
LPT bar in the row 5th, there is an LPT bar, and when we simplify this, we write it LPT.
Okay. That's okay. So if you do it correctly, the output will be different. Okay, so we'll stop today and we'll have next session tomorrow at 10 o'clock in the morning.